everyone. Welcome to Reason with Science. I'm your host Jitendra. This episode is with Geraint Lewis. He is professor of astrophysics at the Sydney Institute for Astronomy. His research focuses on the dark side of the universe, the matter and energy that shapes our cosmos. His books include A Fortunate Universe and The Cosmic Revolutionary's Handbook. His latest book is Where Did the Universe Come From? With the co-author Professor Ferrie. In this conversation, we talk about theory of gravity, quantum physics, Big Bang, expansion of universe, matter, how did the elements form, antimatter, black holes, dark matter and dark energy. Enjoy the conversation, share and subscribe to support the podcast. Thank you for listening. Hi, Geraint. Welcome to the podcast.
Hi there. How's it going?
It's great. I mean, it's since finally we are having this conversation, of course, it has to be great. So once we think of these kind of questions, first of all, it's one of those fundamental questions: where did the universe come from? And thinking from scientific perspective, it becomes even more important because then we kind of go into the fundamental nature of the universe, trying to describe all the forces, the particles which we observe when we are studying the universe. But do you think it presupposes the existence of the universe, or do we have to from the scientific point of view?
No, we don't have to. So, I mean, I think let's just back up slightly, right? So, I mean, the modern topic of cosmology is about 100 years old, and we've learned a lot in that time. We've now worked out that the universe has effectively a finite age in terms of the fact that when we look through our telescopes, we're looking back through time, and so we're seeing further and further. But there is this limit as far as we can see. We run into the cosmic microwave background, etc. So we can't see an infinite amount of universe around us. We're limited to what we see. And the fact that the universe has changed over that time all points to the fact that we live in an expanding universe. And if you run the clock backwards, right, you get to this cosmic origin, the thing that we call the Big Bang. And so as a cosmologist, we understand essentially the evolution of the universe, at least in broad brush terms, over 13.8 billion years, or however old the universe is. But we run into that question of what happened at that particular point. Okay, so there's this big question of was the universe born from a true nothing, i.e. there was nothing before in terms of there not just being there no matter or radiation, but also no space and no time? Or does our universe have some sort of relationship to something that came before? And again, we have to be careful with the word before, because I'm already sort of imprinting my notion of time onto it. It could be more complicated. Or is there a bigger role that the universe finds itself in? And this leads to questions of the multiverse and whether or not we are just one universe in many universes. And in reality, we do not know the answer, in the sense that if somebody says to me, "Oh, the universe definitely came from nothing," or somebody says there's definitely a multiverse, I know that there's no definitely, and I know that nothing in our universe tells us what had to be before, whether it's nothing or something. So yeah, we do not know, and it could be one or the other, or even something more mysterious that we haven't even thought of yet. So it's a very open question about the origin of the universe.
Yeah, I just wanted to leave this thing out there because people ask these kind of questions that, okay, do we presuppose whether universe existed like all the time, or it was finally originated? But that's what you are talking about, that there was an origin, but then there are different theories or models that we are still working on.
We can trace our universe back 13.8 billion years. In the simplest picture, it began then. but we know that the simplest picture is not necessarily the correct picture, and we just do not know what could have come before. I think, I mean, if you polled cosmologists, I think most would be uncomfortable with the notion that the Big Bang was really the start of everything. And there are plenty of ideas that people have floated that, our universe was born from a previous universe, which was born from another universe, etc., etc. Of course, you run into problems with infinities, infinite time into the past, infinite space. But if something is going to be infinite, it may as well be the universe, right? So, or whatever the universe finds itself part of.
Yeah, so the idea that you're talking about, this something from nothing, I mean, of course, there was also a book last decade from Lawrence Krauss. He talks about this something from nothing. But again, this notion of nothing is also quite different among physicists, like how we actually define that nothing, right?
Yeah, I must admit, so I don't mind the book, but some of the praise that was heaped on the book by people that don't quite understand the topic, I have a horrible suspicion that Richard Dawkins said it was it's a book whose importance to cosmology reflected Darwin's importance to evolutionary biology. Yeah. And I think that's way over the top as a statement. So, I mean, the ideas that Lawrence presented in that book are quite correct, that, you could imagine that the universe came from nothing, but that's just one possibility, right? And of course, Lawrence himself runs into issues when you go to the philosophers and you ask them what nothing is. And, the entire notion of a nothing itself is a complicated idea. So yeah, look, it's one of those big mysteries that we have yet to solve. I feel pretty confident that science will solve it one day, but I don't know what the answer is.
Yeah, one of my favorite videos on internet is from Neil deGrasse Tyson, where he talks about nothing. It's a small video on his this Star Talk show. And he's like, okay, what is nothing? So he starts describing it. And it was really interesting because, I mean, of course, we can think of nothing. Nothing can be something like a person not in a room, but then a nothing can be, a vacuum, but then there are still particles. So once we try to define nothing, at the end we end up defining it something, right? That's the actually gist of his video, and it's so interesting.
Yeah, as I said, that's why it's a bit of a minefield when it comes to the philosophy of what does nothing mean, because I said, you can imagine, I can think of an empty box, but then when you start to remove dimensions, right? What if you want to remove space and want to remove time? What does that even mean? It's a topic where many physicists are rather scared to tread because you run into philosophy very quickly.
Yeah. So now if we think of Big Bang, actually, that's the moment that we think our universe started. But if we want to think about that, it's all that understanding. It comes from here, like on this planet, the work that we are doing here about particles, studying particles, particle physics, all different forces, right? So right now, the way I get it, like there are two major theories in physics. One comes from Einstein, theory of relativity and about the gravity, and then the other one, which is developed over like more than 100 years now, quantum physics, right? And another aspect that you talk about, these things, that if you go to any university or academic department, there are two different departments that they don't really care about each other. They are just on their own. So let's talk a little bit about these two theories and why they are important before we go to Big Bang and start talking about where did the universe come from.
Well, I mean, I only just recently finished my teaching here at the University of Sydney, and I taught a course on general relativity and cosmology. And I know that at the same time, the students have been doing courses on quantum field theory and the standard model of particle physics. And as we highlighted in our book, right, is that the students are just given these two separate topics, and there seems to be very little interplay between the two. And so As you mentioned, so general relativity, Einstein's theory of gravity, is a very powerful theory, and it works really, really well. And what it did, of course, is it took the concept of gravity as being a force from Newton, threw that out the window, and then said, right, I'm going to recast the mathematics of how gravity acts in terms of the nature of space and time themselves. So, of course, the famous sort of picture you have is that mass curves space and time, and that curvature of space and time is what we experience as gravity. But there's a key insight in that, which personally, it still sort of gives me a bit of a cold shiver to this day, is that this notion of the equivalence principle, in that you can make gravity disappear, right? So if you are free falling, as the astronauts are on the International Space Station, there's no gravity. Now, in Newtonian picture, you say, oh, the space station and the astronauts are falling at the same rate, so it looks like free fall. But to Einstein, that truly is a situation where gravity has been made to vanish. So already in Einstein's picture, gravity is a bit weird. Now, we also know that there are three other fundamental forces in the universe: electromagnetism, the weak force, which is responsible for some radioactivity, and the strong force, which is the force that binds the nuclei of your atoms together. And the thing that these forces have in common is that they're all written within the language of quantum mechanics. So, of course, in the mid-1800s, we had James Clerk Maxwell, who gave us his famous equations of electromagnetism, united electricity and magnetism. But then into the early part of the 20th century, people realized that you could describe electromagnetism as a quantum field theory. So you basically turn the sort of continuous electric and magnetic fields of Maxwell into these discrete particles, the photons that carry electromagnetic force. And similarly, you can write the weak force in the same language. So, in quantum departments, you would talk about the electroweak force because you can unite them together with the same language. And even you can bring in the strong force. But the difference is that there's no equivalence principle for those forces, right? There's no way you can make them disappear. So the famous case with like electromagnetism is that for an observer, the mix of electric field and magnetic field they observe depends upon their relative motions. But you can't make the electric field and magnetic field completely disappear. So what we have ended up with here, in 2022 is two different textbooks. We have one textbook with Einstein's general theory of relativity that does gravity. We have another textbook, which is quantum mechanics, that does the other three fundamental forces. And they're different mathematical languages. The language of quantum mechanics is not the language of... And that's quite annoying, right? Because one of the key aspects of being a physicist is that, we're very lazy people. We don't want two textbooks. We want one single textbook that could describe the actions of all of the forces. So, you'd want one master equation out of which comes gravity, the strong force, the weak force, and electromagnetism. And, since the 1920s, people have been trying to force these forces together into a single language. And every attempt has basically failed, right? So even Einstein on his deathbed in 1955 was looking at how do you write electromagnetism and gravity into the same mathematical formalism, and it didn't work. And we've now had loop quantum gravity, string theory, and a whole bunch of other theories where people have tried to put together a single mathematical language, and they don't work. And it's very, very frustrating.
Yeah, so the thing about quantum mechanics that you mentioned, so the three forces, strong force, weak force, and the electromagnetism, they are comprised, or we call them something like standard model in physics, which again, we go in the search of a theory of everything, where, of course, gravity is missing. And that's like the alternatives that you gave, loop quantum theory, etc., right?
Yeah. So the standard model, as you said, is like if you ask the physicists what's the toolbox to understand the very small scale universe, right? They would say, oh, there's a bunch of particles. There's quarks and leptons, and of the leptons, there's the electron. And of the quarks, the up and down quarks are the ones that make the protons and neutrons. So those are the particles. And then we need glue to stick them together. And so that's going to be electromagnetism, weak force, and strong force. And that describes all of the atoms and everything going on around us, except for gravity. All right. So gravity is not in there. And so you have to have a separate thing out on the side. And of course, most physicists feel that the standard model isn't complete because our observations of the universe need other things which aren't in the standard model. There's dark matter and dark energy, and there's no natural place for those two in the standard model. So it's thought that we need to expand or unfold the mathematics such that we can, as you said, build a theory of everything. And in that theory of everything, there will be the standard model, gravity, dark matter, dark energy, and everything will be in just the one book, which would make life easy.
Yeah, so as Einstein described space-time, merging space and time together. And so now whatever we see around, which we call matter, right? That's part of that space-time. And all the matter can be described either by gravity or the theory of gravity or by the standard model of physics, right?
Yes. So if I want to work out how gravity acts, right, I have what's known as the Einstein field equations. And on one side is the curvature of spacetime, and the other side is the distribution of mass and energy. And I can put that distribution of mass and energy in, and I get the curvature of spacetime. But that distribution of mass and energy doesn't care about quantum mechanics. It just cares that mass has mass. It doesn't care if it's electrons or quarks or whatever. And in fact, normally when you're dealing with a problem, so I'm talking like as a cosmologist, I'm dealing with the expansion of the universe. So I can write down Einstein's equations, I can solve them, tells me about the universe. That's great. And I can just ignore quantum mechanics completely. Whereas if you're in a lab and you're trying to, bounce lasers and get, particles to spin in a certain way, you use quantum mechanics. And you can ignore gravity. Gravity on those scales is irrelevant. So we just have these two theories and they have different domains, but all of the problems we have come from where we think that these theories actually have more or less equal dominance, right? So in the very early universe, when the universe was very hot and dense, gravity would have been very strong, but so would have the other fundamental forces. So how do we talk about that early stage of the universe when we've got these two languages and we really want to talk about the universe as one mathematical idea? And of course, the other idea, the other place where we have problems is at the center of black holes. So we know that it looks like mass can collapse and we get these black holes of intense gravity, but in the mathematics, the density at the center of the black holes, that goes to infinity. And infinities in physical theories are not real things. And so we think that, really, when it gets really dense, quantum mechanics has to play a role. But if we just try and sticky tape the two theories together, it doesn't work. So we really need the proper understanding of how the forces interact to explain like these places where, all of the forces are extreme.
And one of the reason why gravity doesn't work at quantum level, or we can't really stitch them together, is the fact that gravity is really weak force, right? That we are not able to really kind of translate into that smaller level. Is it the case?
That's partly the reason. So actually, it is the reason, but you have to think about it in a couple of terms, right? In the sense that if you wanted to understand gravity at a quantum level, you'd want to see the effects of a quantum gravity. But anytime you do a quantum experiment, anything is swamped by electromagnetism or the other forces. So we can't do experiments at the quantum level to find gravity. And you're right, that's partly because gravity is weak compared to the other forces. So the numbers go something like, if you take the strong forces being 1, then the weak force is around 1,000,000 times weaker than the strong force. And electromagnetism is around there as well. That might be a bit weaker again. But gravity is down at like 10 to the minus 35, 10 to the minus 40 times as strong. So the gravity is an irrelevant force until you get enough mass and energy together where gravity can start to have an effect. So, we're sitting here on the Earth, and we are basically being pulled towards the center of the Earth by all of the mass of the Earth below us, right? But we're not falling towards the Earth because the electrons in your chair and the electrons in the floor are pushing against each other, and they're supporting you. They're basically canceling out gravity's entire effect of trying to pull you towards the center of the Earth. So yeah, gravity is a really, really weak force.
So when it comes to these two models, size matters. I mean, of course, most of the quantum phenomena that we see, they are at really, really small scale, where we are talking about subparticles of atoms, etc. But when it comes to gravity, these are again on bigger objects, like even us as human bodies would be smaller, right? When we are thinking
Yes.
about.
Yeah. So scale really matters. And in our universe, we sort of know that gravity is a large scale phenomenon. As I said, as we mentioned earlier on, we think that gravity must have an effect somewhere on the small scale, but it's just so we can't measure it. So there's like these two domains where the forces dominate, and there's not really a nice fuzzy area in between, which is accessible, where we can weigh up one against the other.
Yeah, so just one more point here, and then we go on to talk about Big Bang and other important questions. So what about then quantum effects? So when we just go up or increase the size, the quantum effects, they start canceling out each other? Or why we can't kind of have the effects at the bigger scales?
So this is actually quite a complicated question. Why is the quantum world quantum and the classical world non-quantum, right? So why don't I worry that I will diffract when I go through a doorway, because I am built of quantum particles, and in terms of quantum mechanics, I should be able to write down a wave function for myself. The issue is something that actually dogs quantum experiments, right? So if you want to measure a quantum phenomena, you normally have to isolate things from other things, in the sense that in quantum mechanics, you have things represented by waves, and that's all fine. But when things interact, weird things happen with the waves. You get that, and I don't want to go too far down the philosophy of quantum mechanics because it's painful, but you get that, that essentially there's almost like a reset, and then the wave function starts doing its thing again. And the problem that we have as big objects is that all of the particles in your body are interacting all of the time. So it's like they don't have a chance to exhibit their quantum behavior, right? Because the electrons in your body are being attracted by the nuclei. They're constantly talking to each other. Each atom is talking to each other. So the quantum behavior is sort of wiped out. Whereas, if I reached into the screen and I took one of your electrons and I put it in a box on its own, and I ask what happens, I could describe that purely by its wave function, because it's not interacting with anything. So there's a scale where the sheer number of interactions destroys the quantum behavior. So it's a thing called decoherence, that if you want to see quantum mechanics, you need to keep the wave functions in coherence. Yeah, that's the word I'm looking for. But if you start to perturb it a lot, then the wave function just basically becomes a mess, and then eventually disappears, and things look like classical objects. But there's no hard and fast boundary, right? So this is one of the things that people are always pushing up the level by which you can see quantum things by trying to keep things as still as possible. And so what you do is you take larger and larger objects, and you put them through a system and see if you can see their quantum effects. And I'm not sure how large they've gotten now, but I think you can take molecules at least and put them through systems, and you can see interference patterns. And so you could make bigger things as long as you keep them isolated. And it was a while ago I was reading this, but the question is eventually you're going to get to the scale where you can put a virus through an experiment, and it will have quantum effects. And then you have to ask yourself, well, what does that mean for the virus? And I know viruses can't think and they don't have that kind of processing power, but and whether or not they're alive or not is another question. But then a semi-living creature put through a quantum system, what does that mean? What does it really mean? Anyway, again, this is grounds where philosophers love to tread, because there's lots of stuff to sort of dissect here.
Yeah, I'm also interested in quantum biology, and now there are studies coming where they see the effects at the biology level. I mean,
Yes.
I think this biggest scale that I could find is the study on European robins, that how they use Earth's magnetic field to move around. So, but I don't know.
Yes.
I think the quantum effect itself is not measured, but it's somehow some indirect experiment that they could do and show that it is the quantum effect. So
and I've seen more than one discussion on whether or not consciousness is related to quantum aspects of your neurons. But all the brain people I actually speak to, they tell me that your neurons are pretty classical devices, right? In the sense that they build up a potential and fire, that there's not really a scale where quantum mechanics can be playing a role. But of course, the brain is a very complicated place, and we don't understand it. So we don't know yet.
Yeah, so let's take this understanding now at the beginning of everything, which we call Big Bang. So how strong is the evidence for Big Bang at the time being?
Well, let's be very careful, right? So step one is, before asking for the evidence, is what do you mean by the Big Bang, right?
Exactly.
So the problem that we often have in physics is people will use words, and groups of people might be using the same words, but they might mean different things. So the Big Bang, and I hate to reference the TV show because I think it's dismal, but the whole universe was in a hot, dense state. So what does the Big Bang mean? So to a cosmologist, at some level, the Big Bang is the fact that our universe has been expanding and cooling over an extensive period of time. Okay, so in terms of that picture, I think the evidence is pretty overwhelming, right? Because we have direct observations with our telescopes that, you look through your telescope, the universe a few billion years ago looks very different to the universe today. And there are key things that have happened. The obvious one is that galaxies have evolved. They look younger in the past, they look older today, right? So it looks like time has passed and the universe has changed. And there was a famous set of observations done in the 1960s that showed that the level of activity in the universe has changed over time. So these active galaxies have changed, and the density of objects has changed as the universe has expanded, etc. And more recently, we have seen observations like that the universe has cooled. We can measure the temperature of the universe today. We know it's 2.75 Kelvin. And we can measure the temperature of the universe into the past, and we've seen it's warmer. And you go all the way back to the cosmic microwave background, which was emitted about 400,000 years into the Big Bang. And, the universe was hotter again. We sort of understand the physics of that scale. So the universe has definitely expanded and cooled over a very long period of time. And the question is, can that expansion be described in Einstein's general theory of relativity? And the answer is yes, because there are other observations that we can do. One of my favorite is cosmological time dilation. This is the fact that when we look through our telescopes, things are running slower as we see them because of the expanding universe. We can measure that effect. Distant supernovas, exploding stars, they take longer to explode in our telescopes because the light has traveled through an expanding universe, etc. So there's lots of observations that confirm that the universe is expanding, right? And this goes all the way back to Hubble and Lemaitre working in the 1920s and into the 1930s. Then there's the other meaning of the Big Bang that people use, which is this cosmic beginning, right? So clearly the cosmic beginning is part of that cosmological picture. And as I said, if you wind the clock backwards and the universe was hotter and denser in the past, then we can track the physics really, really quite well, because we understand the physics of nuclear reactions and even hot plasmas, etc. We can push back and push back. And one of the nicest pieces of evidence that our universe has gone through this change is what's known as Big Bang nucleosynthesis, right? This is the forging of the first elements in the universe. So at some point, the universe was so hot that no individual atoms could exist, no nuclei could exist. It was just a soup of protons and neutrons. But as the universe cooled, then these things could start to stick together. And we can calculate the rates that these things stick together and what comes out the other side. And this isn't a new thing. This was, these calculations were done in the 1940s and 50s, and they predicted that the universe would be 75% hydrogen, 25% helium, and then just trace elements of everything else. And, we have an object next door, the sun, and we can ask what is it? What is its elemental abundance? And it's 75% hydrogen, 25% helium, and everything else is trace. And it works, right? It's rather terrifying that it actually does work. So the notion that our universe is described by Einstein's general theory, it started hot and dense, it's been cooling ever since, all those kind of things. That picture is overwhelming when it comes to explaining the observations that we have, right? It's the universe we see around us. So, this is when I often get into arguments, because not necessarily with you, because often you give a public talk and there will be somebody in the audience, often a retired engineer, who doesn't like that picture, and they have their own theory of how the universe has evolved. And everything else that has been put on the table doesn't work as well as the Big Bang picture of cosmology as we have it, right? It explains the observations that we have better than any other theory. And that's not to say that it's definitely correct, because no scientist will ever say something's definitely correct, but it is the best that we have at the moment. And it's yet to receive a challenge, which I think would be a death blow for it. It does have things it needs to work on, but it is still the best theory.
Yeah, I mean, I think that's the best part, that the evidence points at this theory and this stands out so far.
Yes.
This also kind of brings, another major question: what is fundamental in the universe, and what was beyond that, right? One notion which is nowadays quite revolving around is space-time is doomed, means there is something beyond space-time. So are we going like in that direction as well when we have to think of origin of universe and Big Bang, etc.?
Yeah, so let's talk about the fundamental makeup of the universe then, right? So as you mentioned, right, we have our standard model, which has got particles and forces in it, and we have gravity, which talks about space and time. And so we can think about those as the constituent pieces of the universe. And the question is there something more fundamental than what we call fundamental, right? So is there something more fundamental than an electron? Okay, is it made of the same stuff as quarks are made of, and really they're just representations of the same thing? So that's the kind of notion that you get from like string theory, is that really everything is made of strings, and it's just the way they vibrate in that makes them look like an electron or look like a quark, etc. When you get into the questions about what space and time are, things become somewhat messier, right? Part of the reason they become messier is that normally in physics, you would say that space and time are your background. So physics is what happens on space and time, in space and time. But relativity says that physics now is also space and time themselves. And people have started to ask the question, well, maybe space and time, if I look close enough, I could dissect those up and find out that they're made of fundamental pieces as well. It's an idea, but it's an idea that that is more hypothesis than it is anything else, right? In the sense that these are all parts of theories of everything, and we know that we don't actually have a working theory of everything. What we have are ideas where people are going in certain directions, and they hope that they aren't going to hit a dead end, and they will find that they find a theory that can explain everything. But all of them are still struggling. I can give you a personal anecdote if you want.
Yeah, sure.
All right. So I started my undergraduate degree in 1987, and I was at the University of London at Queen Mary College. And one of my tutors was a guy called Michael Green. Now, Michael Green, if you've got any physicists listening, people would know that him and Schwartz wrote the first key books on string theory. Okay, so this was 1987, and we were told that any day now that they're going to crack string theory, and we will have gravity, and we'll have all the other forces all written in one language and all this kind of thing. So here we are several years later, and string theory, of course, has now morphed into M theory. And M theory is not really a theory, it's a collection of theories and ideas and approximations. And we still don't feel any closer, right? So, people have been trying hard, and of course we have to, and I'm not knocking the people who work in this area, but it's a hard problem, and we don't know. We said we don't know if strings are the right idea. We don't know if loop quantum gravity, where space and time are little seeds, is that the right kind of idea? We don't even know if the general idea people have is you've got to take gravity and somehow shoehorn that into the other forces, but we don't even know if that's the right direction. What if it's the other forces have to give and become part of this picture more like gravity? We don't know. We really don't know. And so, as I said, if you look at the where people are pushing on the doors of fundamental theory, it's not like everyone's pushing in the same direction. It's everyone sort of pushing in multiple directions, in multiple dimensions, all at the same time, and we still are quite stuck.
But what does this mean? So if we think Big Bang as this t equals to 0, time equals to 0, so at, I don't know, t equals to 0 point whatever 10 raised to the power minus whatever time. So are we talking about what is happening at that time, or we are talking about even like now what is beyond space time?
We're trying to do both, right? So imagine that some smart student somewhere in the world tomorrow wakes up and they just go, that's it. That's how it works. And tomorrow we have a theory of everything, right? So what is that theory of everything going to do for us? Well, it is going to tell us about the fundamental universe here and now, in the sense that it will tell us, is space quantized? Is time quantized? Are particles made of strings or beads or something else? It will tell us what is going on here and now. And what I mean by tell us, of course, what it will do is it'll give us testable predictions. That your experimenter will go to the lab, they'll run their experiment, and they'll say, oh, yeah, look, it definitely agrees with space being lumpy on this scale or something. But what it will also do is it will unlock the doors of the mysterious. Okay, so let's just imagine we've got a time machine. Okay, and we're going to go back to the Big Bang, and we're going to stop on the way. Right. So we start today. Let's go back 5 billion years, and we open the time machine. And what we're going to find is that the universe is going to be somewhat hotter, somewhat denser than today. And we've got physics to describe that universe. It's basically the same physics as today. Okay. Let's go back a few 100,000 years after the Big Bang. Now, the universe was different then because the universe was hotter and denser, but there were no neutral atoms. Okay, the universe was still hot enough that electrons can't join to nuclei. But we've still got physics to describe that because that's just plasmas. And of course, you do a course on plasma physics, it's just the plasma, right? So let's go back now to a couple of minutes after the Big Bang, after t equals 0. Well, now the universe is quite dense. I think it has a density of water, which is quite dense, right? But it's still very, very hot. It's probably around a billion degrees. And you've got nuclear reactions going on. Now, of course, you're going to need a thick coat, right? Because it's going to be pretty hot. But you can describe the physics, right? Because it's nuclear reactions. We know because of firstly nuclear weapons and then nuclear power plants. We understood nuclear physics. Then we go back, let's say, about a millionth of a second, and things are still hot and dense. And we can understand some of the physics, but not all of it. It starts to be, gets to the extremes where physics gets a little bit hairier. Why? Because very high densities, very high energies. Maybe there are some processes there that we see at the Large Hadron Collider. Maybe there's not, right? So we're starting to run out of physics because our physics books are incomplete, right? And we push back even further. So you get back. And we as the further we push back, the less we can rely on our physics textbooks, the more we have to deal with the speculative ideas of physics. So 10 to the minus 34 seconds, there's this notion that the universe underwent this burst of expansion known as inflation, which has left its imprint on the universe today, but we don't understand the physics of it. We think it's related to grand unified theories and forces splitting and all this kind of stuff. But we don't really have the mathematics to describe that, right? So we keep pushing back and we keep pushing back. And, the amount of solid physics goes down and the amount of speculation goes up. And then we get to around this time of 10 to the minus 43 seconds. And essentially, it's all speculation there. We hit what's called the Planck time, which is where we think that that's really where gravity and the other forces have to work together. And we don't have the maths for that. And so, it's all speculation, right? Now, but you say to me, oh, but this is 10 to the minus 43 seconds. What about 10 to the minus 44, or 10 to the minus 50, or 10 to the minus 60? And I have to go, well, I don't know. I don't know. I don't know the physics beyond this point. And I don't know if t equals 0 is really t equals 0, or is it something that connects to the previous universe, right? We just don't have the physics.
Yeah, I think this goes to also a point. So I was listening to a talk of Peter Atkins, a chemist, but he also writes about cosmology and the beginning of everything, etc. So he talks about this circular way of origin of universe. That means there was another universe which existed and which collapses, and we get another universe. So it's just a circular thing, rather than just a starting point and we get one universe.
Yeah, I mean,
again,
that's an idea. There's a couple of cosmologists, Neil Turok and Steinhardt, who have got what's known as the ekpyrotic universe. So this is a similar universe. It's born and it lives and it dies, and it's born and it lives and it dies. There are problems with this picture that they sort of hand wave their way around. So there's this big question of entropy, right? And so that entropy is this measure of disorder, and the fact that your daughter universe will be more unstructured than the parent universe because of the it's very difficult to get rid of disorder once you've created it. So this is one thing that related to Roger Penrose's Nobel Prize, showing that entropy increases even if you go into a big crunch. So you need some magic way of taking away, I shouldn't say magic, you need some mechanism to take away entropy such you can start fresh with a nice universe, which is, starts with low entropy and gives you a chance to form structure, etc. I mean, I don't find those ideas overly satisfying. They sound a little contrived in my mind. My understanding is that for Turok and Steinhardt is that they don't like the inflationary idea, and so they're trying to come up with an alternative kind of picture. But of course, this then is related to, do I have a single universe bouncing along, or do I have lots of universes bouncing along? And before you know it, you've run up straight into a multiverse kind of picture where there are universe upon universe upon universe going on in some sort of larger scale structure. So, yeah, nobody knows. People have had their favorite ideas. People sometimes speak with more confidence than they're due, but nobody really knows what happens because we do not have that theory.
So one thing in the book that you mentioned is, and it was really exciting, that in physics we think a lot about symmetries and shapes. So that's where I was thinking. So how do you envision Big Bang? Do you think of some sort of shape, like it's a center of a circle, or I don't know, of an ellipse, and it just expands, or how do you think of it?
No, not really. So you have to be very careful. So I said I've just finished teaching this, and so when we measure the properties of our universe, okay, one of the things that we measure is the geometry of space. So that's one of the things that goes into the calculations, and it turns out that the geometry of space means that space appears to be flat. And what I mean by that is that the mathematical rules as written out by Euclid a couple of thousand years ago, they hold, right? So right angle, triangle, circles, pi, etc. That holds. Okay. So that geometry holds in the universe. It didn't have to. If space was curved, we would have different geometries. Now, one of the things is that if space is flat, then the simplest flat space you can have is, because you can't have edges, right? The simplest flat space you can have is that it's infinite in extent. Okay, it just goes on forever. And if the universe is infinite in extent today, it was infinite in extent yesterday, and 5 billion years ago, and 10 billion years ago, and 10 to the minus 34 seconds after the Big Bang, it was infinite. And you can just keep going back, and the universe was infinite at all times. So in my viewpoint is that the universe has always been infinite, and the geometry that you're talking about is really about the patch of the universe that we can see, right? So we are a bubble in an infinite universe, and we can see a little part of that universe around us in our bubble, our observable universe. And that bubble's getting bigger at the moment. But beyond the walls of the bubble, there's just an infinite amount of universe out there. Now,
Yeah,
people
I
don't
think
like
that.
that.
No, that makes sense actually.
Okay. Lots of people don't like that because, again, we have infinities. But as I said, if something's going to be infinite, it may as well be the universe, right?
Exactly. I mean,
Yeah.
it's also about the fact that we kind of forget about the scaling factor, because if we are making universe like smaller and smaller, the other particles, they also get smaller and smaller. So at the end, for that one point, it'll be infinite, right? Like
Yeah. So the t=0 part, that's one that can give you a headache. But you're right.
Yeah.
Things were closer together in the past, but in an infinite universe, you can keep bringing things in from infinity, and things get closer and closer together. You don't run out of things to bring closer together.
Yeah. So then if we talk about, if we just go further a little bit from t=0, how did it start? Is it only the quantum mechanics there, quantum physics, or there was also gravity at play? And so before that, the question is, so what is fundamental then? What is so is gravity fundamental? We take it like at, I don't know, t = 10 raised to power minus 34. We take gravity as in acting force, including the standard model, or it changes?
Okay, so again, this is speculation, right? So the one of the things that we find, okay, in our theories is that when you go to higher energies, the forces become very, 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 very similar, right? So let's just start with electromagnetism and the weak force, okay? So in the universe today, they appear to be very different. This is electromagnetism, has something to do with charges, and the force is carried by photons, and photons have no mass. The weak force, though, right, that's related to quarks and electrons, and that force is carried by massive particles called the W and the Z particles. So they look really different. But when we start asking how these interactions appear at higher and higher energies, that difference disappears and they end up looking basically like the same force. So at a certain energy scale, we no longer talk about electromagnetism and the weak force, we talk about the electroweak force. And it appears that as we push further and further, that the strong force will do the same. And there's an idea that if we push even further, that even gravity will lose its distinction. Okay, so this is something. It's got various names. Some people call it the super force, right? But again, it's related to this idea of symmetry and simplicity, right? So imagine, and I'm going to try not to go all biblical on this, right? But imagine the universe is born, and in the very first instant, it's just perfectly simple. There are no distinct forces. There's just the one super force, and the universe is in a pure state, right? But it's expanding and cooling, so the energy is starting to drop. And the first thing that happens, it gets to a point where gravity becomes distinct. So this is what's thought to happen around that Planck scale, around 10 to the minus 34 seconds, that gravity separated from the perfect force. And again, not wanting to get all biblical, but you can think about it like, the angels and the devil, and the splitting between heaven and hell and that kind of thing. I'm not a biblical person, but it's a nice kind of picture. The universe continues to cool, so that after that point, you've got this almost perfect force and gravity now doing its thing. You get to around 10 to the minus 34 seconds, and that's when the strong force becomes distinct. So again, what's left now is you've got electroweak, strong force, and gravity, and the universe cools and cools and cools. And then you get that the electroweak and splits into the weak force and electromagnetism. So you can sort of think about it as the universe started hot, high energy in a state of perfection. It's cooled, and as it's cooled, it's fractured, and it's fractured into the forces that we see around us today. And one of the things that I like to speculate about is that maybe this process hasn't finished. So, the universe is cool today, but in the future, it's going to be a lot cooler. And what's going to happen when, 100 billion trillion years from now, do we get to a stage where, the electric force splits into something else, right? Or the weak force splits because you've finally gotten cold enough in the universe. We don't know, but it's a interesting thing to speculate about, because we sort of think, we make the mistake of, we're here today now, therefore the universe is more or less finished, right? Because this is it. But we forget there's an infinite future ahead of us where things can still happen as the universe changes. So that was a bit of a random kind of description, but that's kind of the steps that we think happens through the Big Bang.
Yeah, but then what causes the expansion of the universe?
What causes the expansion? What causes the expansion is the fact that the universe was expanding to begin with, right? So we're now running into a different kind of question here. And again, this is one that nobody really has an answer to, is why the particular initial conditions for our universe, right? So our universe was born it was hot, it was dense, it was expanding, it was the superforce. Why that combination? Why wasn't it born cold, collapsing, with no forces whatsoever, right? So now you're asking a deeper question, and this runs into another thing I've written a bit of stuff about this question of fine tuning in the universe, right? Why is there life in the universe, and what does that have to do with the birth of the universe? And it runs into this question of why was the universe imprinted with a particular set of physics at the outset? And again, we don't really know. I mean, some people think, oh, that's essentially the only way the universe could have been, which I don't think is a very satisfying answer at all. And then there's other people that sort of say, well, maybe the universe could have been different, right? So if you imagine that there is a machine, a metaphorical machine, that churns out universes, right? But that the way that the universe is churned out, each is imprinted with its own laws of physics. So, in the multiverse picture, that's the kind of thing that's happening, is that something is producing universes, and each universe gets its own law of physics. What's kind of interesting is that we can play games with the laws of physics as we understand them and ask what the conditions in those other universes would be like. And what we find is that most of those universes would be dead and sterile, right? So if you mess around with the laws of physics, let's do a simple one, right? Let's imagine that for some reason in the Big Bang, all matter was formed in black holes, right? There are some people that tell you can create black holes in the early universe, but imagine that all matter was in black holes. So you create a universe that looks like our universe, except there's no free matter, everything's in black holes. I think it's easy to imagine that life in that universe is going to be very difficult, because how do you create life out of black holes? So, any universe that goes down that route is going to be dead. And any universe, and you can play lots of games, you can adjust the masses of the quarks, and instead of the proton being the lowest mass baryon, that particular class of particle, you make it a neutron. So if you imagine the universe was full of neutrons rather than protons, then again, things are very difficult, because neutrons, they don't attract electrons, you don't form atoms. And if you don't form atoms, how do you form molecules? If you don't form molecules, how do you form people? So we run into this question of so we produce lots of universes, and every so often one gets imprinted with the correct laws of physics that allow for complexity, right? Allow for a periodic table, and hence molecules, and hence life. And we should expect to find ourselves in such a universe, and of course we do. But the counter side of that, of course, is that out there in the multiverse, there's an almost infinite number of other universes, and they're dead and sterile. And every so often in between, we'll find one that has the conditions, the possibility for life. But that's a bigger question.
Yeah. Also, the fact that there should be then new universes originating at somewhere, right? Because
absolutely. Then again, the idea of the multiverse is not a single idea. There are different ideas of how you create a multiverse. But yeah, that essentially all of them sort of suggest that this is a process that has been happening ever since, let's go infinity back, will happen to infinity in the future. So it's a process where universes are, popping into existence all through some more complicated structure of space and time, or even something more complicated than that. We can talk about that later, about where the multiverse is. But yeah, it could be that there are an immense number of universes out there.
Yeah. So when we think of, what you are talking about is these constants that we use in physics, which are fine-tuned to our universe in a way that if we change a little bit, of course, the outcome changes, right?
Absolutely.
But then still, I mean, just the existence of those constants doesn't explain the all the diversity of matter that we see on in this universe, like the fact that we have all the different elements, etc. They don't, I mean, they require something else, right? Or it's just those constants, if we take them, we can explain the existence of these elements.
Yeah, no. The all of the elements that we have. So if you let's take an atom, okay? So an atom is it's three of the fundamental forces in action, right? So you have the strong force between quarks to bind quarks into protons and neutrons. And then you also have a residual strong force that binds protons and neutrons into the nucleus. And you have the electromagnetic force, which is holding the electrons in their orbits. And every so often, the weak force will give you radioactive decay, right? So, and the stability of an atom is a balance between those three forces. So, you know the value of stability, right? When you draw the elements and you have isotopes and elements, and you have that there's a band of stable isotopes, and then as you move away from that band, they become less and less stable. So, this is why you don't have carbon with 500 neutrons in it, because that's an unstable nucleus. The shape of that valley of stability is a reflection of the relative strengths of strong force, weak force, and electromagnetism, and the masses of the quarks and the electrons. Right? That's what that is a map of. And if I adjust those forces, right, then I can change the value of stability. So if I make the strong force stronger, I can stop alpha decay, right? I can even prevent beta decay. And so my value of stability will become wider and wider and wider. So I would have more stable isotopes, right? Now, is that a good thing or a bad thing? I'm not sure. I'm not really a molecular biologist, but the shape of a molecule depends upon the masses of the atoms involved and the forces, right? So at the moment we have I can't remember how many stable isotopes of carbon there are, but there's a handful. But what would that do if there were 20 or 30 or 40 stable isotopes of carbon? Right? Each molecule then would be slightly different shape because of the different masses, etc. But I can then also do the following. I can adjust my forces and I can wipe out the value of stability altogether, right? I can make every nucleus radioactive in a sense that it has a lifetime and it will decay. And of course, I can change it such that they decay. It might be 10 years or 1 year or a minute or 10 to the minus 6 seconds. So once you've wiped out your value of stability, what does that do? Well, then you don't have any stable elements around to create molecules. So what does that do for life, which requires stability, at least on some sort of time scale, for life to form? So the value of stability is a reflection of the fact that we are here at some level, right? We are here because of the value of stability in the elements versus isotopes kind of picture. I actually find that is humbling the right word? I don't know. Again, a bit of a shiver down the spine that we are related in that particular sense.
Yeah. So, and then if we talk about fine tuning at the particle level, because at larger scale, we have some flexibility when it comes to these constants. But what about at particle level? So are all electrons the same?
Well, all electrons are effectively the same, but we don't know why the electron has the mass that it does, right? So the electron mass is roughly 1/1800th the mass of the proton, right? So when we have an atom and the electrons orbiting, right, it's the nucleus that dominates. But why is it 1/1800th? Why isn't it 1/18th? Right? Or 1 to 1? Why isn't an electron as heavy as a proton? Now imagine what your atom would be like if that was the case, right? Because instead of the electron buzzing around, everything's going to be buzzing around. Now, can you imagine trying to form molecules out of that? The other example which I like is that, as I mentioned, the proton is the lowest mass baryon. So it's like the building block of matter. And we have the neutron, which comes in, and that gives you a bit of a spacer inside your nuclei, which cuts down on the electromagnetic repulsion. But if I adjust the masses of the quarks and I make the up quark quite light, then the lowest mass baryon becomes 3 up quarks together, okay? And that creates a particle, which is called the delta plus plus. And it's called the delta plus plus because it has a charge of 2. So it takes 2 electrons, right? So it has 2 electrons orbiting. So you might say, well, what difference does that make? Well, what you've done then is, firstly, you've robbed the universe of hydrogen. And of course, hydrogen is very important, okay? And what you've replaced it with is effectively helium. And helium, of course, is the first of the noble gases, which means it's useless, right? You don't get helium bonded to helium or helium bonded to anything else. Its electron shells are full. It doesn't care. So you've gotten rid of hydrogen, one of the really reactive, versatile elements, and you've replaced it with effectively helium everywhere. What is that going to do for the universe? Now, you might be able to get things going, but you might say to yourself, well, wouldn't it be better if the universe started off with hydrogen, which you can do stars with and all this kind of stuff? So yeah, you can easily play around and make a sterile universe by adjusting the fundamental level. And one of my, if I'm talking too much, please tell me to stop. But
no, that's fine. It's good.
Yeah. There's a beautiful example that was pointed out by Fred Hoyle, and it's now known as the Hoyle resonance, which you may have heard of. And this is a property of carbon, a carbon nucleus. So we know how elements are built up in stars, right? So hydrogen goes to helium, and then the next step is, I stick 2 heliums together, that forms beryllium. And then I stick in another helium, and that forms carbon, right? But the problem that we have is that beryllium is a really brittle nucleus. It falls apart very, very easily. And so when people tried to do their calculations, Fred Hoyle was one of the first to do this, to calculate how much hydrogen turns into helium, beryllium into carbon. They found that stars don't make much carbon, right? That stars were very inefficient. They would make beryllium, and beryllium would fall apart, and they'd make more beryllium, and beryllium would fall apart. And so only every so often would a carbon nucleus be made. And Hoyle looked around and went, well, there's lots of carbon, so where does it come from? And what he deduced is that there must be a state of carbon, right, which beryllium can form that will aid it. So you make beryllium, another beryllium comes along, and it sort of slips into this sort of carbon nucleus, which can be sort of semi-stable and then can become a stable carbon nucleus. But all of the nuclear physicists said, now that state, it doesn't look like it exists. But Hoyle was insistent and said, the fact that we have carbon in the universe tells us this state must exist. And he badgered some people to go and look for it. And they found it, right? So that's a nice story, but this state that exists, that is, again, a combination of the electromagnetic and the strong force. And if they were different, that state would be somewhere else. And there wouldn't be this pathway to form beryllium into carbon. And so we wouldn't have carbon in the universe. And of course, carbon is a very versatile kind of molecule, kind of nucleus. There's another thing though, right? Which is not often talked about, is that oxygen doesn't have the same structure to its nucleus. It doesn't have one of these resonances, which is good, because what that means is that when you keep adding particles to carbon, you could turn it all into oxygen, right? So you can imagine that you're producing carbon, but it quickly becomes oxygen, and you still end up with a universe with lots of oxygen, but no carbon. And that's not the universe that we have around us. So the fact is what we've got carbon with just the right level and oxygen without it, which means that we can build up lots of carbon and lots of oxygen, and they become two of the most abundant elements in the universe today. And that's, that's the kind of thing that our life is based on. But if you adjusted the relative amounts of the strong force electromagnetism, you destroy that and you end up with a very different elemental abundance in the universe. So yeah, again, the fundamental forces, we are the fundamental forces and masses writ large, because all of those processes had to occur for us to be here.
Yeah, this is fascinating. And the way you described it, it was amazing. So one thing that you mentioned is that the particles or the elements that we get, the carbon, beryllium, or these elements, they are formed on stars. So that means that probably there was not enough energy, or what are the reasons that they were not formed after Big Bang? I mean, it was after Big Bang, but not like exactly at this 10 to the power minus 34 second, right? It came after.
Yeah. So the formation of the elements didn't start until roughly a few seconds after the Big Bang, right? Because essentially the universe was too hot. And again, there's a funny quirk in our universe. Okay, so I mean, you know your chemistry, right? So you know that if I take a proton and I take a neutron and I join them together, I create deuterium. Yeah. But deuterium is a very weak nucleus. It's only just bound together, and a little flick and it'll fall apart. Okay. But in our universe, I can't take two protons and stick them together. They just don't stick. And I can't take two neutrons, stick them together. They don't stick. So in the universe, the first step to forming elements is to create deuterium. But I've got to wait for my universe to cool down enough for my deuterium to stick, because if I don't have deuterium, I can't build up heavier elements. So there's this thing called the deuterium bottleneck. The universe is sitting there going, waiting for the universe to cool down, and then it cools down and things start to stick together. So things happen quite quickly. You get that you form deuterium sticks together, starts to form helium, maybe a little bit of lithium, but by that point, the universe has cooled down too much, right? So the universe is cooled, and remember, these nuclei, they're charged, and so they can't get close enough for the strong force. They just basically start bouncing off each other with electromagnetism. And so nucleosynthesis, the formation of the first elements, gets cut off because it waited too long, and then there wasn't enough time to build up the heavy elements. Okay. Now, again, this goes into the fine-tuning thing, is why did the universe cool down that quickly? Because the universe could have expanded at a different rate. If the universe expanded really slowly, then you can build up any element you want. You could build up the universe all the way up to iron if you wanted to, turn every element into iron. But it didn't. It was just right to produce some hydrogen and helium, and then it was too cool, and then all the other elements had to wait for stars to come along to create carbon, nitrogen, oxygen, etc. So yeah, many of our elements are from the inside of stars, because nucleosynthesis was inefficient at the start of the universe.
Yeah, and then these elements, they reach, of course, to different planets, because so how does that happen? Does this go into this question of like, how do the stars form, or how do the planets form, etc.?
Yeah. So the important thing to remember is that stars have a life. Okay, so the stars are born from big clouds of gas. gas collapses and you form your stars. And some stars will be small and some stars will be big, right? And that dictates their lifespan, right? So big stars, you get lots of squeezing from gravity, so the cores get very hot. So their nuclear generators in the core, they run very, very fast. Small stars, a little bit of squeezing, their generators run very, very slowly. So the sun is it's not really a mid-sized star, but it's not a tiny star. And so its lifespan is going to be around 10 billion years. And so in the middle of the sun right now, it's turning hydrogen into helium. Later on, when it gets a bit older and runs out of hydrogen in its core, it'll start burning helium into some heavier elements, and that will change the structure of the sun. And what that means is that when in a few billion years' time, because the internal structure of the sun changes, the sun starts to swell and starts to grow. And so it becomes what's known as a red giant. And it will get big enough, it'll swallow the orbit of Mercury, get bigger again, swallow Venus, bigger again, it will swallow the orbit of the Earth, bigger again, it might even get out to the orbit of Mars, maybe, right? But it undergoes these pulsations. It's very unstable. Like it is getting to its old age. It's getting cranky. We understand all of that, right? and that material basically eventually gets blown away. Right now, that material that used to be the atmosphere of the sun has been enriched with some of the elements that were made in the core. Right, so the elements have flown out, and so that gas goes back out into the interstellar medium and into the gas clouds, which will form the next generation of stars, right? Now, for bigger stars, it's even more dramatic because they might live, instead of 10 billion years, they might only live 10 million years. And in their cores, because their cores are so hot, they can fuse, carbon into silicon and silicon into et cetera, up through the heavier elements into iron. So they create iron in their cores, right? And when they reach that point, one of the interesting things about iron is that in terms of nuclear reactions, it's endothermic. You have to put energy in to make iron do stuff. So you make a core of iron, and in a fraction of a second, the core goes out, right? So you stop your nuclear reactors, and the star, which has been supported by that flow of energy outwards, collapses inwards and crushes the core. And then that superheats the core. So that then fuses iron into heavier elements like gold, right? And then the star rips itself apart and explodes. And again, that material gets spat out and goes to the clouds of interstellar medium and go into the next generation of stars. So we already know that our sun, which is roughly 5 billion years old, right, was formed from gas that was polluted from generations of stars that came before, right? So the carbon inside your body, the gold inside this ring, etc., has already been through the life cycle of at least one star, but possibly many stars, right? So, if it's gone into a series of giant stars, right, this is what's happened, and the gas gets polluted. And so, so our sun was born from that polluted ball of gas. And I said we can see those trace elements in the atmosphere of the sun. And we are born, the Earth is just the leftover rubbish that was in the disk. So when the gas cloud collapses, starts off roughly as a ball, slowly spinning, but it collapses down, it produces a disk. In that disk, stuff sticks together. So eventually you form rocks, and rocks stick together. In there, the Earth was born, and the elements from which we are made were part of that original rock, plus other bits that fell in later on. So again, I actually think it's quite sobering to think about where the atoms in your body have been, right? And where they will go. Because, humans have a fairly short lifespan. And I think we already acknowledge that we're going to be recycled in the biosphere of the Earth, right? So who knows where you'll come back in the future, if you'll be a daisy or something else, or your carbon might get locked up in coal or whatever, or into a diamond. But eventually there's going to be a recycling on a solar system scale, right? Some material will be left here in the cinder of what was the Earth. Some material will be blown out into the interstellar gas, and your atoms might find themselves in a living creature that's, a trillion years from now, which is kind of weird. And of course, might not just be in one creature, you might end up in multiple creatures, right? Spread around the place. You just don't know. But yeah, so there's this just recycling of the elements and material as the universe ages.
Yeah, so the ancient, like in our previous generations, people used to say that when you die, you become a star. So I think it's also the other way around. Probably once the star dies, maybe the life forms, they can come out of them, right?
Yeah. Oh yeah. Yeah. I really like that thought that my atoms have had that. It's this thing, right? You think about yourself and your existence and your consciousness, and you forget that the physical body is made of atoms and they come from somewhere. And of course, they're continuously replenished, right? I mean, the atoms that are you now, most of them are not the atoms that you were born with. Right? You've grown. Where did they come from? So there's this recycling of atoms, and you forget that the consciousness is basically just driving around in this meaty vehicle, but those atoms have had a life of their own before you existed.
Yeah, it's fascinating.
Yeah.
So let's, since of course we are talking about this nice and interesting thing, we can include a villain in the picture, if it's a villain, called Antimatter. So this goes to, again, this fundamental question: why is there matter at all, right? Because once we conceptualize, or once we think of antimatter, which is again antimatter, and it should basically merge with matter and finish off, or just leave radiation out, right?
Yeah.
Yeah. So
it's an excellent question. And again, if we go back to that notion near the Big Bang, we talked about simplicity and symmetry. We would have expected that there should be equal amounts of matter and antimatter in the universe. And as you said, as the universe cools, that should completely annihilate, and we should be left with just radiation, right? So that's clearly not the case. And we can actually work out, right? In the early universe, there must have been matter and antimatter produced. We can actually work out what their relative abundances were, right? So we have the cosmic microwave background radiation, okay? And what we know is that for every proton that we have in the universe, there is about 1 billion photons in the cosmic microwave background, okay? And what this tells us is that those photons, which came from the annihilation of matter and antimatter, that tells us that in the early universe, that for every 1 billion antiprotons, there were 1,000,000,001 protons, right? And so that when they annihilated, there was the one proton left over, okay? So we have an asymmetry in matter and antimatter. And the question is, where did that come from? And it's a peculiar question, because when you look at the laws of physics, they don't distinguish between matter and antimatter, right? So let's take electromagnetism. If I took an antiproton and a positron, which is an anti-electron, and I made an anti-hydrogen atom, it would behave exactly like a normal hydrogen atom. Electromagnetism doesn't care about matter or antimatter. It just doesn't care. And so your anti-hydrogen would absorb photons and emit photons. They wouldn't know any different. And it's the same with the strong force, right? The strong force doesn't really care about matter or antimatter either, right? So where does the asymmetry come from? And there's only one culprit left, and that's the weak force. And in my humble opinion, the weak force is the most interesting force in the universe. So let's just transport ourselves back to the 1950s, okay? So people have been looking at the fundamental forces, and they realized that the weak force was a thing. And there was a famous paper that came out in 1955, 56, 55, by two physicists, Yang and Lee. And they looked at the various forces, and they said, yep, we can see that electromagnetism and the strong forces, they're well behaved, but we're not sure that the weak force is. And one of the things that they suggested is that the weak force might violate something that's known as parity conservation. Are you familiar with parity conservation?
Yeah.
Yeah. So parity is this notion of, simply put, is that if I look at the universe in a mirror, the physics that I see going on in my mirror is, I could see that in my universe if I looked around enough, right? So again, if I look at a hydrogen atom in our universe and in the mirror, everything looks fine. But the weak force doesn't obey that rule, okay? So there was a famous experiment done just after this paper came out by Wu, and her experiment was basically took a bunch of cobalt nuclei and put them in a magnetic field, made them really cold, so they're all spinning in the same direction. So cobalt nuclei spin, and she was looking at radioactive decay. So you had the weak force in action, and so that spits out a positron or an electron. That's what you get from the weak force, right? Now, if you imagine that I've got a hydrogen atom and it's excited and it's going to emit a photon, right? Then that photon can be emitted essentially in any direction as long as the rules of quantum mechanics are obeyed. And one of the key rules is to do with the fact that photons spin, right? So atoms spin, the electrons spin, etc. Photons, when they get emitted, they spin, and all of the spins have to add up, because you can't break this rule of all spins must be the same. But photons can spin in two different ways, right? They can either spin clockwise in the direction of motion or anti-clockwise. So if I've got my hydrogen atom and it emits a photon, well, it could emit this one spinning this way, or one spinning that way, and it would still obey the conservation of all the spins. So I couldn't guess which direction the photon was going to come out of, right? And it's the same with the strong force. So again, in the mirror, I see photons coming out both ends, and I see photons coming out both ends. But the experiment that Wu did, right? If the weak force played the same game, then we'd expect to see the same things for the electrons that we've been spat out. Now, electrons spin, and you could imagine that they spin in clockwise or anti-clockwise. And so if I've got my nucleus, I could either have an electron spin it this way or go out that way, spin in the opposite direction. So I should expect electrons to be coming out, in various directions. Everything should be fine. But in the Wu experiment, found that the electrons only came from one side, right? So why is that? And the answer is that in the weak decay, there's not only the electron which is spat out, but there's another particle. And that particle is something called the neutrino. And unlike every other particle in the universe, neutrinos only spin one way, right? So they know clockwise, and they're all made spinning clockwise. And so in that mirror view of the universe, right, where you're looking at your cobalt nucleus, because it's a mirror view, it appears to be spinning in the opposite direction. So the electrons are coming out of the wrong side in the mirror view compared to our universe, right? So yeah, the neutrino turns out to be the source of essentially the start of this notion that the universe has got an asymmetry written into it. And there was and actually one of the nice things, which not many people know, is that Yang and Lee got the Nobel Prize for their work, and they got it basically 1 year after they published their work. Now, remember, Einstein had to wait, almost 20 years to get his Nobel Prize. That's how earth-shattering the fact that the universe essentially knows clockwise from anti-clockwise. It knows the difference. And then in the 60s, there was a series of experiments by Cronin and Fitch using these particles called kaons that found that the weak force actually violated other symmetries as well that people thought were bound to be obeyed. So it's something called, I'll let your listeners look this up because there's far too much to talk about. It's called CP violation, charge parity violation. And that they violate this rule as well. It's something that was thought, now this can't be broken. So there are asymmetries in the universe related to the weak force, but they're not big enough to explain the matter-antimatter asymmetry, right? So there's something else that we're missing in the laws of physics, another asymmetry in there somewhere that meant that matter got dominance over antimatter. And what we mean by that, right, is that you can imagine we've got some reactions, okay? So like let's pretend we've got an electron and a positron, and we crash them together, and they spit out something, right? That for some reason that reaction produces slightly more matter than it produces antimatter. Over time, you will build up the asymmetry. We don't know where it comes from, but it's got to be hidden there somewhere in the rules of physics, because if it's not, then why are we here? We should just be a sea of radiation.
Yeah, and does dark matter or dark energy may have to do something with it, or?
Again, we're not really sure. So we don't know when dark matter was created or the process through which it was created. What it looks like, I mean, if you think the inflationary picture is the correct description of the universe, then it looks like matter was created at the end of inflation. There was this flood of energy back into the universe, something called reheating. And that flood of energy created the source of the particles that became protons and neutrons today. And it was probably in that process that dark matter was somewhere in the mix, or at least the particles that decayed into what became dark matter. I don't really know. And it's thought that dark matter basically played a bit of a background role in the early universe, that it didn't interact and it didn't produce this asymmetry. Now, doesn't mean that it didn't have a role. Maybe it did, but we can't find a definite sign for it playing a role in the early universe. Dark energy, nobody has a clue. Nobody has a clue. We don't know where it came from, when it arrived. There are speculations that so there must have been an energy in the universe during inflation. It's called the inflaton, which is, physicists are rubbish at naming things. So there was this energy called the inflaton. Some people have speculated that burst of energy in the early universe hung around and is now becoming dark energy today. Others think it's quite separate. Others have tried to tie dark energy to things like the Higgs field. We don't know. Dark energy is the real problem in cosmology in explaining its existence. Why it exists in the first place, why it has the energy density it does, and what's its role? What has it been, for the first 5 billion years of the universe, dark energy was irrelevant. It was invisible. So why is it becoming apparent now? And I think in my mind, this is related to this thing that the universe hasn't finished yet, right? That things will happen as the universe cools, and this might be one of them, and that other things will happen in the distant future, a little bit like dark energy come to dominate. Maybe something else will appear. It's very low level today, but will appear as a dominant feature in the distant universe.
Yeah, that just brings this question of emergence, which especially it's much more problematic for chemists and biologists, is why something emerges. And when
Yeah.
it comes to complexity, it's just, yeah.
Yeah.
No.
I mean, I know that there's the traditional description of physics, chemistry, and
Yeah.
biology,
Yeah.
right? And that physics is somewhat fundamental, or whatever, however you want to call it. But in reality, physics just does the easy stuff,
Yeah.
right? And what you've got is complexity working your way upwards, where the techniques used by physicists no longer apply. And I remember Martin Rees, who's the astronomer royal in the UK. I remember him at a talk pointing out that a star is much simpler than a bumblebee. Right? We can understand a star. We can write down the equations of a star. We can work out the life of a star. But you can't work out why a bumblebee is going to go to that flower or that flower, because it involves brain processes, even though it's a teeny brain, and they're beyond us.
Yeah, I think bumblebee is far complex. Even bacteria, for example, we can't really.
Yeah. Oh, yeah. Yeah. I think he was just being poetic because bumblebees are out in the sunshine.
Yeah. So there was this one interesting question on Twitter once I posted about our chat. It was about the angular momentum, if it gets included in dark matter models of galactic rotation. It's a bit technical, but what's your what's your idea about that?
Well, the answer is yes. I mean, we look. So we've got dark matter, and so again, if dark matter is a physical substance, right? So if you imagine if it's a physical substance and we don't have angular momentum, then what's going to happen? Well, all that mass is just going to go and collapse down, right? So the fact that our mass doesn't collapse tells you that it must have motions that support it, okay? And so there are really two kinds of motions that dark matter could have. Either it could be that everything is just zipping around doing its own thing. So you can imagine, actually, there's an example. There's groups of stars called globular clusters. So these are roughly 1 million stars, and they're bound together by their own gravity. They hold themselves together. But each star is doing its own orbits, right? So it's moving around, and they all stay roughly spherical, but they're bound together by their own gravity. So dark matter could be like that. Could be just stuff zipping in and out, right? Or you could have that, and you could also have a net rotation. So the entire dark matter sort of mass is rotating around as well, because that provides support. That's the reason why the Earth doesn't fall into the sun, is that we have angular momentum with respect to the sun. So we do include it. I mean, it has to be there. And when we do our computer simulations of the formation and evolution of galaxies, things move around depending upon what gravity is doing, and things spin up, etc. So angular momentum is there. We can't neglect it, because angular momentum is the one thing that's stopping dark matter collapsing down to be a point, right? So this is the reason. Okay, so you may have seen a picture of a galaxy where you've got the Milky Way. It's got a flat disk with a little bit in the middle, and then there's a big dark matter halo, which is kind of spherical around it. And don't be misled by the word halo. Halo doesn't mean that it's thin. It means it goes all the way into the center, right? And the question is, well, why is the galaxy flat and the dark matter out here? And the answer is because the physics of dark matter and the physics of gas are different. Because the gas started out roughly spherical as well, but gas can do things that dark matter can't. Gas can cool, gas can collide, so you can lose angular momentum, and gas can fragment. So what actually happens is that in our roughly spherical starting orientation, gas can collapse into a disk. But dark matter can't. It can't lose its angular momentum because it can't collide. So the only way it can lose angular momentum is through gravitational interactions, and that's really, really slow. It's, because it's such a weak interaction. It's very difficult to pass angular momentum from here to here if it's only through gravitation. So you need other forces that allow you to do that.
Yeah. So with our understanding, what do you think? One day, can we create our universe?
Oh, well, that's a good question. And again, I think it's related to the theory of everything, right? I mean, if we really do understand the true nature of space and time, we may get to the stage where we can manipulate space and time, right? So you can think about it. I mean, we could easily manipulate space and time by just moving stars around, right? But let's say we want to manipulate it at the fundamental level. Well, what that means is that you're packing energy and mass into particular regions, and you might be able to do that to such an extent that you create a black hole or something. And there are people that have speculated, and I've forgotten who wrote the book now, that essentially that the formation of a black hole is a way that you could produce space and time, which is expanding elsewhere beyond our universe. So it might be possible. I mean, it's hard to say it's impossible, given the laws of physics as we know them. It might be that it is truly impossible. It might be that it's practically impossible, that we might say, oh, we could do this theoretically, but we can't actually do it. But we can't rule it out. I think it is, still in there as a possibility.
Okay, that's fascinating. So this has been great. It was a great conversation, and I mean, thinking about 3.8 billion years of universe, I think we have, we might have given that 10 to the power minus 34 second kind of time to initiate this kind of conversation, and so people can start thinking about those deeper questions from scientific point of view, which is amazing. So thank you so much.
Oh, thank you. It's been great, and I'm always happy to talk about the universe.
Yeah.